Alright, so let's talk a little bit about functions. I'll just start with some of the basic terminology, just in case we forgot. Functions basically some kind of map from one set A to another set B, whatever. It's kind of an abstract picture of it. You should use F. Well, you can use whatever you want, I suppose. And so we write this for this picture. Function from A to B. A is called the domain of F, so that's the set of allowed inputs. B is called the codomain. Now that's not quite the set of outputs. It's a place where the range is found. So the range of F is equal to F of A. Alright, and that is going to be F of X such that X is an element of the domain. Alright, so that's the range. The range is a set of possible outputs. Now, by and large, in calculus we study what? We study what are called real valued functions of a real variable, right? So real valued functions of a real variable we can describe a couple different ways. We can describe it by a formula, right? F of x can be given, right? And you can describe it by a graph. Those are the sort of the two main ways. Now, I would say there's kind of a third way, which is it's F of x for x in the domain of F. So in other words, we can choose a specific domain for the function. Let's see here. So, for example, let's see here. So, excuse me. If we have f of x equal to, say, x squared plus 1, then what's the domain? Well, if we just say that, then the domain is all x for which this makes sense. When does x squared plus 1 make sense? Well, yes, it does. Okay, so the domain of f is equal to the reals. The range of f, right? So you can think about this one actually. If you plug in real numbers into this formula, what happens? It's always 1 plus something that's non-negative, right? So the range of f is pretty clearly 1 to infinity. And, you know, as a second example, let me say this example number 1, example number 2. We could give the same formula, right? But then we could say the domain of f is, say, I don't know, how about this, 0 to infinity. Alright? Now the funny thing is, if you think about it, the range of f is still the same. Maybe I should call these different things. Let me call this f2. Alright? Since these are different functions technically. You say they're different functions, but they have the same formula. How can they be different functions? Well, okay, it's not a big deal. If you look at the graph, right, what does it look like? Well, this one versus that one. Sorry if this is boring, but we just need to settle a few issues here, make sure that we're aware of these. Not always a big deal, but it's better if we know about them. So this one, of course the y-intercept is 1, and it's just this guy, right? This is the so-called graph. This set of points is the graph of f, right? What's the graph? Graph of f is, what is it equal to? Well, the graph of f is actually equal to the set of pairs, x comma f of x, right? Such that x is in the domain of f. I think I'm off the margin here. Oops. Alright, well let me just pan up a bit. There we go. So that's, you know, generically that's what a graph of is of a real valued function, right? Set of pairs, x from the domain, f of x the output. Alright. So we can actually visualize the graph as a particular curve in the plane. Fine. You guys know this. Now the difference, of course, between the graph of f and the graph of f2 is pretty significant, right? The graph of f2, on the other hand, is just this, right? See, because the domain starts at 0, goes to infinity, and well, the range of both of these goes from 1 to infinity as it happens. Now, one of these functions is not like the other. Let's see here. Quick calculation. One of these functions has an inverse, right? So what does it mean to have an inverse? If we have f, right, g of f of x equals to x, and if we have f of g of y equal to y, and this is for each x in the domain of x. So here x is in the domain, right? The y, where are the y's? Well, the y's are in the range of f, right? If you have this situation here, like this, then this function g is related to f. It's said to be the inverse function of f, right? We usually write g is equal to f inverse. That's the inverse function. All right. So one of these functions has an inverse function, one of them doesn't. Now, if you try a way to find the inverse function is pretty simple. Operationally, what do you do? Well, you can just basically you write down the equation for the graph, like this case, y equals x squared plus 1, right? And then you try to solve for x. So this says x squared is equal to 1 minus y, which then says x is equal to, well, plus or minus the square root of 1 minus y, right? And so that plus or minus is really troublesome over here because both of the solutions, plus or minus, are both allowed, right? For this, there's also that. In other words, this graph fails the horizontal line test, right? In the sense that there's two inputs which lead the same output, right? So this function does not have a global inverse. In contrast, this guy, we can choose the plus, right? And we get f2 inverse of y is simply equal to the square root of 1 minus y. So it's pretty cool. This function's invertible, whereas that function's not. The inverse of this function I can even draw if I'm so foolish as to attempt such a thing. You do what? You draw the line y equals x, and see every one of these points flips over, right? This point 0, 1 becomes 1, 0, and you just kind of symmetrically reflect the points across the line y equals x, and there you go, there's the graph, right? This is actually y equals f2 inverse of x. All right. If you want to plot them on the same point, you notice that the domain of f2 is 1 to infinity, and the range of f2 is 0 to infinity, right? It mirrors the domain and range of the given function. So that's how a function and its inverse are related. All right. So let's see here. So what we really are interested in is a few specific sort of standard examples, right? So these standard examples, you need to know what these standard examples are. You need to know how they behave, right? So one of the first standard examples that we're always looking at, that always comes up, is the so-called exponential function. I mean, we talked about polynomials previously, right? So those are interesting, but the exponential is really, an important example. So basically, f of x equals to a to the x, and here a is some constant greater than 1. For the sake of this discussion, this looks like basically what? Just it goes through a of 0 is 1, and its graph looks something like this, very crudely speaking, right? Now, you guys remember, so there's different a's which are important. Like, suppose this was a equals to 3, right? I can also graph 2 to the x. That would be what? Something like down here. Then 2 to the x. Between these two, of course, is the infamous or famous, whatever you want to say, exponential function, right? The exponential function. I can't draw it worth anything. So here, this green line is y equals to e to the x, which is special, right? E is 2.71, something like that. It's, as you know, flash forward, right? D dx of e to the x equals e to the x. That's what makes it so special. It's got the value, its slope at each point is equal to its value at each point, right? That's the exponential function. Anyway, we can say this: the domain of a to the x is equal to the whole reals, right? Which we could also denote minus infinity to infinity. The range of this function, if you'll allow me this common notation to use the formula to define the function, slightly bad math, but we know what it means, so I guess it's not too bad. 0 to infinity. All right. Clearly it passes the horizontal line test, and maybe you remember, what's the inverse function? Well, the inverse function, if we want to find the inverse function, we look at y equals a to the x, and you want to isolate x, right? So let's see here. What I would do is I would take the natural log of both sides. So the natural log of a to the x, all right, great. That's x ln of a, and there you have it. X is equal to ln of y over ln of a. That's the inverse function, right? So, like, in other words, if f of x is equal to a to the x, then f inverse of y is equal to the natural log of y over the natural log of a. Now, maybe you also remember that there's another way of writing that, right? The change of base formula. For logarithms is what? The natural log of y over the natural log of a can also be understood to be log base a of y, right? Of course, you also know that you can think of this in one step, right? We could start with y equals a to the x, take the log base a of both sides, and we get x equals to log base a of y. So there you have it. There's another way to look at the formula. F inverse of y is log base a of y. All right. So that's a little bit. There's not really much to say here. You need to know the domain. The main fact about an exponential function that you should know, without flinching, is that exponentials are positive, right? And so if you know that, that'll help you out a lot. All right, so that's the first standard example, an exponential. The next standard example, I would say, is something like f of x equals to, let's say, the sine function. What's sine of x? Well, I'm just going to introduce it by its graph, all right? So the sine function, what does it look like? It looks like this, right? So let's see here. What's important to know about this sine function? It's stuck between these two vertical lines, right? Like it's stuck between plus and minus 1, right? Up here, you got y equals 1. Down here, you've got y equals minus 1. If you go 2 pi forward from any point, you get back to the same output again, right? In other words, there's a fundamental identity for sine. The sine of x plus any integer multiple of 2 pi is equal to sine of x again, right? That's true for any k in the integers, k an element of z. This is a fancy way of saying k is equal to, like if I wanted to expand that and write it in a less elegant way, I could say 0 plus or minus 1 plus or minus 2, but it's just a lot less writing to say k is an element of z. All right, so important questions about sine, of course. The domain of sine x is what? Well, the domain of sine x is the whole reals. What's the range of sine x? Well, it's minus 1 to 1, right? Included. And let's see, other important questions you might ask about sine. Where is sine 0? Let's see here if we can say that in an elegant way. Sine of 0 is 0 here, 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 here. That's pi, that's 2 pi, that's 3 pi. And that's 0. You need my phone. Oh no. All right, let's see here. I guess I'll allow it. There you go. All right, so in short, sine of x is equal to 0, the solution set to this, right, if and only if x is an element of basically pi times z. Now pi times z, I just introduced some new notation for you. That's kind of a slick notation. This is the set pi times n, which by the way is n pi. I usually write it n pi. I don't know why I wrote it pi n. Anyway, doesn't matter. Such that what? Such that n is a integer. So integer multiples of pi is where sine is 0. All right. Now, all right. So, is there an inverse function for sine? I guess is the next question you might ask. Well, there's of course there's different. Okay, this is the thing you guys get confused about. There's two different notions of inversion, right? So, the one is just the multiplicative inverse, and that's we talk about that less, but right? I mean, and that's not what we mean when we say inverse sine. I mean, the multiplicative inverse of sine is 1 over sine, right? So like 1 over sine x is what? 1 over sine x, by the way, is not equal to inverse sine. That's just, I mean, I know it's hypocritical on our part because we say we don't, this is not true, right? But we do have that sine squared of x is equal to sine of x squared. I mean, it's not my notation, but it's common notation, so we have to deal with it, all right? And I'm going to use that notation because that's the common notation. Some people, instead of saying this, they'll say something like arc sine. All right, in part to avoid this confusion. But I won't, because it should be clear from context which kind of inverse we're talking about. So this inverse sine is the sine that works like this. So we have sine of sine inverse of y, all right, is equal to y again. And that's for minus 1 less than or equal to y less than or equal to 1. So I can only take the inverse sine of something that's in the range of sine, right? But then here's where the ambiguity comes into play. Sine inverse of sine of x is equal to x. That's not true for all real numbers, all right? So this is only, now this depends on the definition of inverse sine. So basically the inverse sine is the inverse for what's called a restriction of a sine. If you take a function, all right, and you take its domain and you replace it by a smaller set of numbers, this is what's called a restriction. So the restriction of sine that's considered for the inverse sine is this. We go from this point to that point, all right? So you could say that that's f restricted to minus pi over 2 to pi over 2, all right? That of x is, I know it's kind of awful to look at, is equal to sine of x, right? And you're like, well, what happens to this thing outside of minus pi over 2 to pi over 2? The answer is nothing. It doesn't exist. I mean, this function is defined only for this little restriction of sine. That's the definition of inverse sine, is that it's a so-called local inverse of sine. It's a inverse for sine restricted to this particular closed interval. So, by definition, this is only for minus pi over 2 less than or equal to x less than or equal to pi over 2. All right. Okay. Apparently we're playing... What are we playing? I don't know. It seems to be in Mandarin. Alright, so anyway... Sorry, Matthew's trying to distract me. Definition. So that basically defines the inverse sine. Alright. So, it only spits back x when it's in the appropriate place. Let's see here. For example, if I asked what was inverse sine of sine of, I don't know, let's say 3 pi over 2. All right. Then it would not be equal to 3 pi over 2. What you have to do is you have to use, I mean, one way to think about it anyway, here's the way I think about it. I know that sine is 2 pi periodic, right? So I have to find the angle which it falls in this range. So if I subtract 2 pi from this, I get minus pi over 2. And then I'm like, ah, okay, well, there it is. So that's minus pi over 2. All right, very boring. Inverse sine always outputs things in this interval of real numbers, because it's not an inverse for the sine function, it's an inverse for the restriction of the sine function to this particular interval. You're like, well, why? That's our choice. That's the definition. All right. You could choose otherwise. You could make it go other places if you wanted to, but then you'd have to make your own calculator to do that or whatever. All right. So that's sine. Cosine. If you look at cosine, the story repeats itself here. Much the same story, right? F equals to cosine of x. It's just a little bit different than sine, right? It starts at 1 and then it does like this again, right? Again, the domain, I won't go into all the details here as much. Domain of cosine x is the reals, right? The range, again, of cosine x is still -1 to 1, right? It's still bounded. All right. In other words, we have this like really nice inequality, right? Like -1 less than or equal to cosine x less than or equal to 1. The places where cosine are 0 are a little bit more complicated, right? So like we have zeros here and here and here and here and here and here, and they're not so nicely arranged as the last time, right? So I got like this pi over 2, right? And then this is pi over 2 plus 2 pi, and you know this one is pi over 2 plus 4 pi, and so forth. On the other hand, right, we've got this other series of zeros, sequence of zeros, I suppose, minus pi over 2, right? And then this one is minus pi over 2 plus 2 pi, right? Here's minus pi over 2, minus pi over 2 plus 4 pi, and so forth. Let's see here. So, I don't know. I guess I haven't thought about it for a little while, but let's see here. I suppose if I was asked, what's the solution set, right? If I want to solve cosine of x equals to 0, what's the solution set? Well, that's true if and only if what? X is equal to, one slick way to write it would be this. Plus or minus pi over 2 plus 2 pi k for some k in the integers, right? Let's see here. If you want to write it, if you like what I did in the other answer, you could also say this: x is an element of what? It's an element of pi over 2. It's supposed to be pi over 2. Pi over 2 plus 2 pi z union minus pi over 2 plus 2 pi z. You could write it like that if you're so inclined. I don't know, this doesn't have much appeal to me. I think I kind of like this expression up here more. It seems to be more to the point. I mean, but this appeals to me as well. Alright, so there you go. Those are the zeros of cosine. Now, when you talk about inverse cosine, of course, the global function cosine fails the inverse line test, right? And horizontal line test, I should say. So when we talk about inverse cosine, we're talking about cosine restricted to a particular interval. In this case, this. All right. So oh, I'm sorry. Oops, that would not be the standard restriction. Oops, strike that from the record. Let's see, we are going to restrict cosine to, over here, I'll do it in purple, this piece right here. So if we look at f restricted to 0 to pi, all right, so that restriction, so it's same formula but different domain. On that, just that little bit right there, all right, it passes the horizontal line test, right? There's just one output for every input value. I mean, well, there's always just one output for every input. I should say there's just one input to obtain. Oh, I can't say it. If you pick any particular output, only one input maps to it. All right, there we go. All right, anyway, so getting more to the point, definition. Let's see here. First, the easy part. Cosine of cosine inverse of y is equal to y. That's true for minus 1 less than or equal to y less than or equal to 1, whereas cosine inverse of cosine of x is only equal to x again when it falls into where the definition of cosine is made. In other words, where we restrict cosine to this little subinterval, x has to be in there if we're going to get back x again. And so that's only true for 0 less than or equal to x less than or equal to pi. All right. And that's the definition. Again, I could do another example, but I'm not going to. All right, so there's inverse cosine. Another important example, of course, tangent. F of x equals to tangent x. Tangent x is sine x over cosine x, right? Pretty neat function. Oops, I think I'm outside the boundaries here. All right, let me get back inside here. So that tangent x, it has vertical asymptotes where it's got division by 0. So like, well, it's interesting. The range of tangent x is the whole real line. The domain of tangent x is kind of interesting, right? It is equal to the reals minus the zeros of cosine. That set, right? So if I just talked about it up here, I don't want to try to write it again. It's this guy. All right. Those points are missing. Those are where we have vertical asymptotes at plus or minus pi over 2, right? And so forth and so on. So tangent, it turns out, has a periodicity. It repeats itself every pi. Right. So like we have the equation, an important equation to know about for tangent, sometimes useful, is that tangent of x plus n pi is equal to tangent of x for n in the integers, all right? So that's an important property of tangent. It has this pi periodicity. Now, its graph looks something like this, all right? And so forth, and it keeps repeating, and it's very boring. It just keeps repeating itself forever and ever. And so, of course, if you were to draw a horizontal line through this graph, I'm sorry, I'm using the wrong pointing device. Here we go. If you draw a horizontal line like so, you cut through tangent here and here and here, and lots of places, and that won't do. So we can't find an inverse for a global inverse tangent. However, if we focus our attention on just this central part of the inverse tangent of the tangent, then there's an inverse tangent for that, and that's where we define definition. So first of all, tangent of inverse tangent of y. Well, good news. That's equal to y, and that's for any y, for y in the reals, because the range of tangent is from plus to minus infinity, right? However, going the other way around, the tangent inverse of tangent of x is only equal to x again for minus pi over 2, not included, less than x less than pi over 2. That's just the definition, right? So if you try to use inverse tangent to get an angle which is outside plus or minus pi over 2, it isn't going to do it, right? Inverse tangent will always tell you an angle between plus or minus 90 degrees. And so you shouldn't be surprised when inverse tangent doesn't find angles for you outside of quadrants 1 and 4. Oh, so many points. So many points have been lost over this simple comment. But anyway, all right, so that's exponential sine, cosine. Next up the list, of course, will be hyperbolic sine and hyperbolic cosine. Since those are a little bit less familiar, I'm going to start the next video on those. Thanks.